Okay, I think we recorded now. Okay, looks good. Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked mathematics questions at both the high school and early college or university level. If you're interested in getting help with your homework or if you're interested in tutoring, check out the links in the description below. Cool. So, let me switch over my screen real fast and we can do some mathematic magic. Math is always a good time. Okay, and like this. Okay, cool. So let's get this party started. So our first question is asking us, what is an asymptote? Now, an asymptote in math is an asymptote. This is kind of like a graph, or in a graphical sense, because this is typically the best way to visualize it. It's kind of difficult to think about it in like a purely numerical sense. In a graphical sense, graphically, it's where a function approaches but never quite gets there. They are usually caused by or there are a couple different types. Before I mention what their causes are, there are vertical, horizontal, and I think it's how do they call it? Oblique asymptote. So these are diagonal. And of course vertical asymptotes, horizontal asymptotes are vertical and horizontal. Yeah. Now what causes vertical asymptotes are typically caused by values with undefined outputs. Example, dividing by 0. And horizontal asymptotes, they're like the least special out of all of them. They're typically, you can see a horizontal asymptote just like if you substitute in a very large number, you can typically find it. And for diagonal asymptotes, these typically come from rational functions. Typically come from rational functions. Okay, cool. So these are what asymptotes are, and as we can see from our from the answer that we have so far, is that visually they kind of look like this. So an example of an asymptote, an example of a vertical asymptote . An example of a vertical asymptote would be y equals 1 over x minus 1. Okay, you'll see that when x is equal to 1, y equals 1 over 1 minus 1 equals 1 over 0, undefined. So the function is undefined at x equals 1. And of course, you know, that's just for this particular rational function. But if you had something like x minus 5 underneath, you would see that x equals 5 is what leads to a divide by 0, which is where it's undefined. So what this would look like on a graph is like this. So here are our axes. That's our y-axis and our x-axis. Suppose here is x equals 1. We would have a vertical asymptote like this. So this would be vertical asymptote. Asymptote at x equals 1. And our graph would look a little something like this. So over here it would be going down to the negatives, and it would be looking like this. So they're going different directions on the asymptote for this particular function. And if we were really to zoom in onto what's going on here, if this is the asymptote, this is the asymptote, you would see that like it's pretty much on the line, never exactly on the line, but pretty much on the line, and further and further down, or you'll get farther from it. So you can actually try this on your calculator. If you try to do like if you do x equals 1, it's not going to work out. You're going to get it divided by 0, and that's, your calculator is not going to appreciate that, and all of the math in the world is not going to appreciate dividing by 0. But if you did like x equals 0.01, you would get that, oh, that's a fairly large number. X equals 0.0001, you're getting an even bigger number. Let's actually write that out to kind of demonstrate what I'm trying to say here. Oops, let's zoom back in. So x equals 1.01, x equals 1.001, x equals 1.0001. In this case, y would be equal to 1 over 1.01 minus 1, which is just 1 over 0.01. And I think that's 100. I'm going to double check my calculator. 1 divide 0.01. Yep, that is 100. This equals 100. If we get even closer, we'll get y equal to 1 over 1.001 minus 1. This equals 1 over 0.001. That's equal 1,000. And 1,000, because it's just like 10 times bigger than the previous one. And the next one, well, this is going to have y equals 10,000. So you see, the closer you get in value, like the closer that your x value gets to the asymptote, the further up is going to be. So it's like they're always increasing towards there. We're never going to be quite able to reach x equals 1, because at least the divide by 0. But that's nothing to be too concerned about, because this asymptote is kind of showing what would happen around there. And on the other side, so on the negative side, maybe let's put it on in green. Oops. If we had like x equals 0.9, here's like 0.999. Here we would have y is equal to 1 over 0.9 minus 1. That's equal to 1 over 0.1, which is equal to 10. But for 0.999, that's going to lead to y equals 1 over 0.999 minus 1. And that's going to lead to 1 over 0. These should be negative on the bottom. My bad. That's negative 10, which is why on the graph here you see that is going downwards, is going deeper into the negatives. Here on the blue side, which is on the right side of the asymptote, we're getting deeper and deeper into the positive region. For the green, on the left side of the asymptote, we're going deeper and deeper negative. Okay, so that's why over here we'll have on the denominator negative 0.001, which is equal to negative 1,000 because of the negative downstairs. Okay, so Um, when you detect that you have a vertical asymptote, kind of a good check is to, if you do a process like this and you check the values that are not quite the asymptote but fairly close to the asymptote, you can see which way is the function going to go on either side of the asymptote. Now there's some other ways that you can do this, but if you put it in your calculator, you'll never get it wrong, because as long as your function is written out properly, this will always be the case. Okay, so that's cool. Now, another thing that we can see is horizontal asymptotes. So this is a vertical asymptote. Typically, you'll have things rising up towards infinity or going down towards infinity. I'll actually write that out so that it's a little bit more clear. Vertical asymptotes have the function going up/down to plus minus infinity, either positive or negative infinity. It depends on your function, on at least one side. Now, the example that we saw here is one-sided. I mean, it's two sides. So on both sides of that asymptote, we have the function. It's defined on both sides, and there will be that. But an example of a one-sided vertical asymptote is log. So if we have y equals log of x, our function is going to be like this. Here's going to be 1, and our function is going to look like this. Okay, so the asymptote at x equals 0, and it's undefined for negative x. Okay, so this would be an example of like a one-sided vertical asymptote. I think it might be only log, or if you have piecewise functions that say like, okay, on the other side of this value, like it's illegal. These are typically when you're going to see vertical asymptotes. It's when you have logs or piecewise functions. Okay, and now for horizontal asymptotes, they work pretty much in the same way. So horizontal asymptotes So this is pretty much what the function approaches. As input approaches plus or minus infinity. Okay, let's see some examples of some horizontal asymptotes. So if we have example y is equal to, let's say, e to the power of x, e being Euler's number, it's really just 2.718. The actual value is not really important. It's just to show that on an exponential graph like this, or an exponential function, so here we have x, here we have y, which is equal to e to the power of x. Here we're going to have 1. Our function is going to look a little something like this. So here, there's no horizontal asymptote on the right side. As you go towards positive infinity, there's no horizontal asymptote because, well, it's not approaching a particular value. The function is not approaching a particular value. It's approaching infinity. So here, there's no horizontal asymptote on positive side. But on the negative side, there is. So if I redraw this to like kind of be a little bit more zoomed in, it does get closer and closer. So the horizontal asymptote on the right side, or on the left side, towards the negative side. So horizontal asymptote on left side, because as x approaches negative infinity, y approaches 0. And you can see this, like you can do, sub in a very, very deeply negative number for x, like e to the power of negative 1,000. You'll see that it's pretty much 0. And these are how horizontal asymptotes approach. An easy way to find horizontal asymptotes. So, easy way to find horizontal asymptote. Like this method is actually so easy, it might even be math teachers everywhere hate me for letting you in on this secret. Just sub in really big numbers. Like try negative 1,000 and then negative 5,000. If they're pretty much the same, you know that on the negative side there is a horizontal asymptote. If there's a significant difference between them, well, there isn't a horizontal asymptote. It's not approaching something. Likewise, you can, on the positive side, if you can sub in a really big number, like a million, and then maybe sub in another number, 2 million, if they are approximately even in their results, when you sub it into your function, you know that you'll have a horizontal asymptote. So sub in really big numbers and see if they're close to some particular value. If they are close to a particular value, if so, that's the HA. Okay, awesome. So that's horizontal asymptotes covered. And the last type of asymptote that we got is oblique asymptotes. So oblique, you might also hear them as diagonal asymptotes. And these are not really related to the obliques, which are on the side of your stomach, which are your ab muscles. They look exactly as you would see them on this here graph that we have on the right. So they have an equation instead of just like for a horizontal asymptote, it'd be like y equals the horizontal asymptote. For a vertical asymptote, it's x equals the vertical asymptote value. But for oblique asymptotes, since they're not perfectly vertical or perfectly horizontal, they are defined by a linear function. So defined by line, that's where linear comes from, defines by line with form y equals mx plus b. They typically emerge from rational functions. Emerge from rational functions. Where the degree of the top or of the numerator is 1 more than the degree of the denominator. The important part is that it's 1 more than the degree of the denominator. Now, what is the degree? The degree is the highest power. Highest power. So, for example, like x cubed plus, or let's say 3x cubed plus 2x squared plus 3. This area has a degree 3. And that degree 3 is because of the power 3. The biggest power, that's the degree. It's really that simple. Okay, so to find the equation of a oblique asymptote, equation is just equation of oblique asymptote is simply the result of the rational function treated as a division, or treated as, yeah, I guess it is just treated as a division. Okay, so that's why it's important that the degree of the top, the degree of the numerator, is only 1 bigger than the degree of the denominator. That's the only possible way that you'll have a result that is a linear function, something that is a form y equals mx plus b. Otherwise, you'll have the result of that division will be something that is not linear, and of course it's not going to correspond to a oblique asymptote, which is a it's a straight line. Okay, so as you can see on the diagram here, the asymptotic behavior is pretty much the same. Like, it's just going to approach it, but it's never going to quite get there. Okay, so yeah, that's how you would visualize like a oblique asymptote, but they really only emerge with rational functions that maybe look something like this. So maybe you'll have like example of something with oblique asymptote. It would be something like this. So perhaps we have y equals, let's say, 3x cubed plus 2x squared plus x minus 2. And then on the bottom, maybe we have like x squared minus 5x plus 6. That would be an example of a function that does have an oblique asymptote, because you see the degree of the top is 3, the degree of the bottom is 2. 3 is only 1 more than 2, so if we do the regular division of this, we would find the equation of the oblique asymptote. Okay, and yeah, that's pretty much exactly what they would have here. Vertical asymptotes, they come from where the function is not allowed to have that particular input, typically caused by divide by 0 or logarithms. So this would be like what a vertical asymptote looks like. They could be two-sided or one-sided. Horizontal asymptotes, they're really just what the function approaches towards negative infinity or positive infinity. So if you just sub in really big numbers, you can find them quite easily. And yep, that's what we have in our diagram here. Just sub in really big and really deeply positive and deeply negative numbers, and you should be able to find a horizontal asymptote. If they match up, like try multiple really big numbers. And then oblique or diagonal asymptotes, well, just look at, they only emerge from rational functions, and do the division. If the top is 1 degree bigger than the bottom, then you have an oblique, otherwise no oblique. Okay, cool. So that would be a brief explanation, a brief rundown of how we can get an asymptote. And yeah, so this above solution is good with good examples. Yeah. So here, solution is good. Awesome. Okay, so the next question that we have on the menu today is asking us, what is concave down? Okay, so let's actually kind of describe what it means to be concave in the first place. So think about the word concave. If we look inside, we have a cave. Inside the word concave, we have the word cave. And we know caves are like, they're like holes, right? So they're like, you know, you can crawl into a cave. Bears live in caves. So these are like kind of like holes. So this would be like the concave region. If this is like, I don't know, maybe this is like deep in a forest somewhere, and this could be a cave. This would be a concave. Convex, on the other hand, is like the opposite of concave. So convex on the, I guess, so there's no, I mean, concave, there's the word cave that can kind of give us a hint. For convex, well, you just kind of got to remember that it's not concave, so this would be like on a hill. On a hill. So like this, on top it would be convex, but underneath it it'd be concave. So yeah, so this is the what it means to be different. Basically, convex is like you're on a hill, concave is like you're in a cave or a valley. And when it says something is concave down, that means the concaveness of that curve is down. So here, this would be an example of concave down. And this would be concave up. And this would also be convex up and convex down. So concave, convex, immediately opposite of each other, so that if you have one, you can find the other. And yeah, if concave down is pretty much like the valley part is opening up downwards. So even though it kind of looks like the direction that you say concave is, that's where it's opening towards. Okay, so if I'm opening my doors towards the down, it's concave down if I'm the concave part. So yeah, but some functions have areas that are concave and some areas that are convex. So like if we have a wave here, a wave function, we can have like concave down until about here. Between there it's concave up. Between there and there it's concave down, and then this section is concave up. So a function is not exclusively one or the other. It's like there are most likely going to be some sections that are concave down, some sections that are concave up. So it's up to you looking at your function to kind of determine exactly how that's happening. Okay, so here's a great example of a function that does have some concave up sections in red and some concave down sections which are in blue. And yeah, this is a great visual experience of this. And this solution is good. And of course, like what is representing this wave could be like position. It could be anything that you choose. It could be position, your excitement level, your income. It could be whatever property that you choose. That's the beauty of math. The basic principles of math are true in any type of situation that you apply them in. It's just up to you to make sure that it's all set up properly, and it will always work out. So here, the above solution. Okay. So the next question that we got on the menu today is asking us if the cosecant of theta is 4 divided by 3, what is the sine, the cosine, the secant, the tangent, and the cotangent of this function? Okay, so let's first talk about the relationships between cosecant, sine, cosine, secant, tan, and cotangent. Okay, so if we write out cosecant, that's what we're given. This is equal to 1 over sine theta. Okay, in this case, the result of the cosecant is 4 over 3. And since we know that sine theta is the reciprocal of cosecant theta, we know that sine theta has to be the inverse of this, which is just 3 over 4. So equal 3 over 4. Okay, now let's talk about the others and how they relate to each other. So here we have, well, First, let's square this off because this is going to be one of the things that we need. That was like the first easy one that we get into, because on the real, this stuff is not too hard. It's fairly straightforward. If I'm being 110% honest about it, it's fairly straightforward. Okay, now let's actually draw out a right angle triangle, maybe something like this. And we can use this to help us get some clues on just knowing what we have so far. How can we proceed? Okay, so if here we have our theta, we have 90 degrees here. Here we got our hypotenuse, hype, our opposite, our adjacent actually, ADJ, and our op. Now we know sine theta is equal to opposite over hypotenuse, and that's just 3 over 4 in this case. So that means op must be 3. So this got to be 3. And adjacent, ADJ, nope, not adjacent, hypotenuse must be equal to 4. So here we got 4. Now, with the power of Pythagoras' theorem, we can try to get ADJ. Or not try to get, we can absolutely get ADJ. So we know that with Pythagoras' theorem, let's just call it h squared, hypotenuse squared, is equal to adjacent squared plus opposite squared. Let's just say p for opposite. If we wanted to solve for adjacent, well, we would just do the square root of hypotenuse squared minus opposite squared. So that's adjacent. And in this case, hypotenuse is 4 squared minus the opposite, which is 3 squared. So we got the square root of 16 minus 9, the square root of 7. And that's A. Okay, so the adjacent is going to be the square root of 7. Square root of 7. Awesome. Okay, it would be more formal to say plus minus the square root of 7, but since we're thinking about this in terms of a triangle, we can just leave it as a just the positive value, because you wouldn't have a negative adjacent length, right? That wouldn't make too much sense. Okay, now using the powers of SOHCAHTOA, we can, and we know all the side lengths, we can find out what cos and tangent are. So we know that cos theta is equal to adjacent ADJ over hypotenuse, and adjacent, we just found that, is the square root of 7 over 4. That's the hypotenuse, and that's cos theta. Okay, now something that we know about cos theta, you know how cosecant was the inverse of sine theta? Well, secant is the inverse of cos theta. Okay, so we have secant is equal to 1 over cos theta, which is equal to pretty much just the inverse of root 7 over 4. So that's just 4 over root 7. Okay, and this would be secant of theta. 4 over root 7. Okay, awesome. And then for tangent, we know that tangent is equal to opposite over adjacent, op over ADJ. What's our opposite? That's 3. Our adjacent, root 7. And that would just be tan theta. 3 divided by root 7. Ain't that a nice simple thing? And if we want to take the reciprocal of tangent, 1 over tan theta, well, that's just equal to cotan theta. And that's going to be, well, it's just a reciprocal of root 7 over 3. So it's going to be, or that's exactly what it's going to be. The reciprocal of 3 over root 7 is root 7 over 3. Okay, so we have 1, 2, 3, 4 down here, and then our let's write down the sine theta is equal to 3 over 4, and cosecant theta is equal to 4 over 3, And the entire party is here. Everybody. So we got the cos, the secant, or we got the sine, the cosine, the secant, the tangent, and the cotangent. And we found all of them with just knowing the given cosecant, knowing the angle, and using the power of Pythagoras and thinking about this question in terms of a right angle triangle and SOHCAHTOA, we have found all of the required things here to make this question work out. Okay, pretty cool stuff. Pretty cool stuff. Hopefully we have the same conclusions down here. Yep, so cos is root 7 over 4. They got plus minus here because they're being a little bit more formal and they're not thinking about it in terms of a right angle triangle. I would say it's better to think about it in terms of a right angle triangle in this particular case because if they're not specifying that this is going to be a part of a function, generally it's going to be about triangles, but it's not wrong to have the plus minus. It would always be plus if you're thinking about it in terms of triangles. Secant, another way, this is really just the same thing, 4 over root 7. You could write it as 4 times root 7 over 7. That's the same way as writing it. I prefer to write it this way, but other people would prefer to write it this way, so it's your call. You could write it either way. And then 3 over root 7 for tan, root 7 over 3 for cotangent, and sine is just an inverse, so that should be 3/4 is sine theta. Yeah, exactly. Exactement. Très bien. Very good. So here, the solutions are good. The above solution is good. However, the plus/minus would not be necessary if this question was thought up of in the sense of a right angle triangle with SOHCAHTOA. Don't forget SOHCAHTOA, it's always there for you. Cool. Okay, so we can keep it moving on to the next question that we got on the menu today, which is asking us, how do we evaluate sine of 2 pi over 3? Okay, so sine 2 pi's divided by 3. Now, this is a radian value. And generally, or at least for me, I learned degrees for angles way before I learned about radians for angles. So let's actually try to think about what this would look like. So let's draw out our Cartesian grid just so that we can have our angles. So if here is 0, this is also 2 pi, because going a complete 360-degree rotation is 2 pi radians. That means halfway through, that's 1 pi. And we got pi over 2, because that's halfway between 0 and pi. And halfway between pi and 2 pi is 3 pi over 2. Yeah, 1.5 pi's. Okay, now what we have here, it says that we have 2/3 of a pi. So we're basically 2/3 of the distance between here and here. 2/3 of the distance, well, that's about like this. So the angle that we got here, this would be 2 pi over 3. 2/3 of a pi, so that's 66% of the way there. And on the other side of this, we're just going to have pi over 3. Because pi over 3 plus 2 pi over 3, those should add up to pi, and they absolutely do. Okay, so we could see that we could also think about this in terms of in terms of, instead of doing sine of the actual angle, which is above 90, we know that we can just do the sine of the corresponding angle that's below 90, in this case pi over 3, and adjust the sine, like the plus minus sign, of the result of the sinusoid function, and we can do it that way. So if we just do, because it's in this quarter, so top left quarter, we can also think about, like, what does a sine graph look like? Sine, it looks like this, and like this, and this would be pi. So it's positive from 0 to pi. This would be a sine x graph, and negative from pi all the way up to 2 pi. Okay, and that's just by looking at the graph. Yeah, so you can see, since it's less than pi, it's between 0 and pi, the result has to be positive. Okay, so sine 2 over 3, sine 2 pi is over 3, not 2 over 3, 2 pi is over 3, is really equal to sine pi over 3. Right? This is the RAA. Not RAR. RAR. RAA, this is the related acute angle. The related acute angle is always going to have the same magnitude as the actual result of the regular sinusoid, and is always taken with respect, big respect, to the x-axis. Okay, so this is one of our, like, things that we should definitely know, like sine pi over 3. Something good to memorize, because it is, I believe it's root 3 over 2. Exactly. So this is just one of our basic trigonometry things that we need to memorize. So sine pi over 3 is equal to the square root of 3 divided by 2. Okay, and yeah, that is precisely what the answer is. And you can see that we got it by doing the related acute angle, just by visualizing this. And we know that we can do, the result is positive, because if we look at the graph of the sine, it's always going to be positive between 0 and pi. When it's between pi and 2 pi, that's when it's going to start to be negative. That's when we got to put in the negative term. So if this was like maybe 4 pi over 3, the result would be negative, because 4 over 3 pi, that's between pi and 2 pi, so that would be a negative result. Okay, so yeah, this the above solution is good. Mention of or visual demonstration of quadrants and why it might be positive or negative would be helpful. Okay, cool. But the answer is good. Definitely root 3 over 2, because that is one of those things that you gotta remember. Okay, cool. So the next question that we got on the menu today is asking us, what is the derivative of secant squared of 2x? So it's pretty much asking us d over dx. That's just asking for the derivative of secant squared, and 2x is the I'm hoping that's the argument to it. Typically you would want brackets around here, like this, but I'm going to assume that that's what that means. Another way that we can write this to make it a little bit more clear as to what is really going on here is, this is secant 2x multiplied by itself. So squared like that. So we're just moving the square outside. This can make it easier to kind of visualize what's going on. Another way that we can write this is, I'll put this in a different color. Since we know that secant of let's say secant of x is equal to 1 over cos of x, what we can do about that is we can substitute in there, because cosine is a little bit easier to take a derivative of instead, because off the top I don't know what the derivative of secant is, but I definitely know that cosine, the derivative of cosine, is negative sine, so that'll be easier to deal with. Okay, so knowing this, let's substitute out that secant to look a little something like this. So d over dx of 1 over cos x, as the same as secant x, but that whole thing is squared. And we can rewrite this, instead of 1 divided by cos x, we can do cos x to the power of negative 1. So d over dx of cosine x to the power of negative 1, and the whole thing to the power of 2. Now we know that we can combine those exponents, the negative 1 and the negative 2. We just add them together, or multiply them together, to get what is really going on, which is 2x. My bad. Oops. I actually need to erase this to make this a little bit more clear. So this should be cos 2x and cos 2x. Okay, yep, good thing we caught that early as opposed to late, because, catching mistakes later on is very painful. Okay, so then we can multiply the exponents together. So we just have d over dx of cos 2x to the power of negative 2. Okay, and that is a much easier, in my opinion, it's a much easier derivative to deal with than the secant squared 2x, because this is just like a chain rule situation. Okay, so now with the power of the chain rule, we got something like this. Okay, so d over dx of cosine of 2x to the power of negative 2. This is equal to, well, we're going to multiply down the top, so that's going to be negative 2. Okay, and then we're going to subtract 1 from the power here, and keep the insides the same. So I'll put it in square brackets, cos 2x to the power of negative 3 now, because we subtracted 1 to it. And now we have to multiply this by the derivative of the internal here. So the derivative of cos 2x. Okay, now let's put this on an additional line. So we got negative 2 cos 2x. And now we have to take the derivative of cos 2x. So we know this is another chain rule situation. So we're going to take the derivative of the outside of here. So that's going to be a negative sine of 2x. And then we have to multiply it by the derivative of 2x, d over dx of 2x. And this is really just 2. So we can write it out like this. This will be negative 2 cos 2x. Actually, this negative becomes a positive. So those two become that. Those two negatives become positives. And multiplied by sine 2x. And this is multiplied by 2. So this is just 4 cos 2x sine 2x, and that would be our final answer. Okay, so this is the derivative of secant squared 2x. It is 4 cos 2x sine 2x, and we've shown the process here with the chain rule, but twice. Okay, let's see. Hopefully the answer here corresponds to that. Okay, so the answer that they had here is secant is now we have to check if this is if the answer that they had here is equal to the answer that we got. So this is 4 secant squared of 2x times tan 2x. Now, are these equal? We're about to find out. Okay, so we know that secant of x is equal to 1 over cos. And we know that tan of x is equal to sine of x divided by cosine of x. Okay, so knowing these, let's sub these in. So here we're going to do, I forgot to add the power of -3 on the cos x. Whoops, that's a good thing that we caught that. So to the power of -3 here, and here to the power of -3, power of -3. Okay, so given this, we can, let's actually substitute the left side of what I calculated versus what is given in the solution here. So let's sub out that cos to the power of -3 with secant cubed. Or actually, before, let's send them all downstairs so we can get the tan. This will work out. Okay, so we can see why here. So this is equal to 4 sine 2x over cos 2x. But this whole thing cubed. Whoops. Cubed. Okay. Now this becomes 4 tan 2x over cos 2x squared. You see how one of those coses we sent it out and then divided it by, or is the divisor of sine, so that becomes a tan on the upstairs. And then hey, well, we send those coses upstairs and we get 4 secant squared of 2x tan 2x. Okay, so as we can see, we get precisely the same answer if we go with my method of changing it into cos first, or with the method here. And I guess if they know the actual derivative of secant, it'd be a lot easier. But since I didn't know off the top, you can always convert them and it will always work out. It just, you got to be very precise with your motions. Like me, I almost forgot that to the power of -3, and that could be a tragic mistake. So just make sure that you stay on point with all of this. And yeah, the above solution is good, but I came to the same results with a different method, but that should mean that the above solution is good. Okay, cool. Okay, the next question that we got on the menu today is asking us, what is secant x equal to in terms of sine x, cos x, and tan x? Okay, so here we got, well, secant cosine of x, or cosine, sine, and tan are all related to like the other, they're cousins through reciprocals. So I'll do like I'll do like basic trig. So we have sine theta, cos theta, and tan theta. Think back to so ka toa with this little diagram here. So we have our adjacent here, our opposite, and our hypotenuse. Our SOHCAHTOA triangle, that'd be a good way to remember our basic trig stuff. And our inverse trig functions are as follows. Inverse trig. So here we have cosecant, CSC of theta. That corresponds to 1 over sine theta. Cos would be secant, which is written as sec. You can put brackets there or not brackets. It's up to you, as long as you are well aware of if there's brackets and what not brackets. And this is equal to 1 over cos theta. And here we have cotangent, C-O-T, cotangent. And that corresponds to 1 over tan theta. Okay, now, do we even need the inverse trigonometric operators anymore? Do we need them? Not really, because they are really just defined. Now they're defined in terms of the reciprocal of the basic trig, but way back in the day, before we had calculators that could fit in the palms of our hands, we were doing calculations by hand, like all the time. Now it would be nice to have inverse trig functions, because back in the day they would have big long tables of like, imagine a table like this, like at 1 degree, sine 1 degree is equal to this, sine 2 degrees equal to this, sine 3 degrees equal to this. Like they have these massive tables corresponding to all possible angles. And, it wasn't always easy to calculate the reciprocal of those answers. So they made the inverse trig tables to make that process a little bit easier, because sometimes you do need the reciprocal. And back then you had to do it like by hand, manually calculating it, instead of doing it with a calculator, which is quite error prone, which is not great. So that's why we have inverse trig in the first place. It's kind of like an artifact of history, but we don't really need it anymore, but still see it in your math programs. Why? Because we don't want to get rid of it formally. There's too much history behind it, and we don't want to lose our history. So to answer this question more directly, secant corresponds to cos, and it's important to know the relationships between the trigonometric functions, the basic trigonometric functions, as well as the more complex inverse trigonometric functions. Okay, so here we can mark that the above question here is good. Or the above answer, is good. Awesome. Okay, now I'm kind of running out of time, unfortunately. I would love to keep going with the mathematic magic, but I do have a schedule that I do need to follow rather strictly. So let me just switch over here, and those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you'd like to submit your own question, also consider visiting the links in the description below. Remember to leave a like if you really enjoyed the video, and leave a comment telling us about how you think about the video. Share this video with your friends if you really enjoyed it. And this has been Millan from OneClass. I hope to see you again soon. Bye now, take care, and remember, mathematic magic is always a great time. Bye now, take care.